my name is Suresh Naidu. I'm a co-director with Ira Katz-Nelson and Katharina Pister of the Center for Political Economy, which is hosting this event together with ICERP and the Program in Economic Research. And we're here to sort of talk about Doyne Farmer's book, The Edge of Chaos, Making Sense of Chaos. Sorry, there's another. I'll just say, before I went to economics grad school, I was a student at the Santa Fe Institute summer school on agent-based modeling. So I learned about, complexity economics, I think, before I learned mainstream economics. And so it's always been something that's like lurked and been interested and tried to make models work, failed. And so I'm sort of really was very fascinated to read Doyne's book and kind of this like retrospective of a career making these kinds of models and making a pitch for why they're just better than what we do in mainstream economics. And so I was like,
say that. You said that.
Well, I don't know. I think you've come pretty close to saying that. And so I was really sort of curious. And and for those of you PhD students in perspectives, you'll if I haven't done it yet, I will. But I'll always do like one or two like half lectures about just like the physics approach to economics and kind of offer it that it's out there and you should know something about it. So I'm really sort of excited to be able to have offer this conversation. So I was excited to have Doyne present his book. And so with that, I think I'll just, and I'm very grateful to both Alma and Mike for joining as discussants. And I think both will provide kind of really great perspectives on the topic. So take it away.
Okay, thank you, Suresh. I think I'll go up to the podium. Let me thank everybody for being here. Given the times, I want to express solidarity for the students and faculty at Columbia. And, today, more than any time, you can't say that economics isn't really, really important. It's great to see capitalism doing its job, not just punishing stupidity, but also actually helping democracy for a change. So, okay. By the way, how many people are in the room would call themselves economists? Okay, give me a feeling for good. So there's my book. There is the US version of the book. So I think that what I'm writing about is a scientific revolution. And why do I use that word? It's a big word because we're really going back to making a change in the foundational way that economics is done. That is saying, deriving models, theoretical models. I'm not here to talk about econometrics, or I'm talking about how theory is built in economics, and focusing mostly on macro and finance. But it's a revolution because you're really going back to a foundational principle like utility maximization and saying, well, maybe we can start somewhere else. I've lived through a few revolutions, chaos, complex systems, and I'm machine learning. And so it's exciting to see this one moving forward, and I'm curious to hear what the panelists are going to say, and I really thank them for doing this. And just, there's a lot of stuff in the book I'm not going to talk about today. I like ecology, and I think it's a useful way to think about the economy because the economy is about specialists, and ecology is a theory of specialists. I talk a lot about endogenous business cycles and chaos. I'm not going to say that here. I think that's the only way to understand endogenous business cycles. I do a lot of stuff on the financial system, which I probably know the most about, but I'm not going to talk about that here. Talk about game theory and how we can learn things from the weather or the way we predict the weather and the energy transition. So those are all things I'm not going to talk about. I think most of you probably know what economic theory is, but since not everybody raised their hand, I at the risk of boring people, in a standard economic theory, you assign agents a utility function. It describes their preferences or their goals. You then give them a model of the world. It could be rational expectations or something else. You assume supply equals demand, and you assume each agent selfishly maximizes their own utility, using their model to take everything else they know into account and realizing the other agents are doing the same. You write down mathematical equations and you deduce the decisions that each agent will make, and you calculate the economic consequences. So I'm going to talk about a different way of doing that same thing. Complexity economics, which is applying complex systems thinking and methods to economics. What does that mean? Well, I was one of the founders of Complex Systems and had a group at Los Alamos in the 80s doing that. And a sort of way of attacking these things has evolved that's in line with the way people do things in lots of other branches of science too. You study complex systems is a study of emergent behavior, and typically, to understand it, you have to model things at fine scale. You have to get down to some form of individual building blocks, and then you simulate typically the way they interact, get some feeling for what they're doing, and then you think, is there some theoretical theory we could do to describe this in a simpler way? So, roughly speaking, that's what we do in complexity economics. We typically make use of simulation. We mimic systems on the computer. We used what are called agent-based models, which are simulations involving decision makers. In the book, I mention a bit about how simulations taken over most other fields of science, physical science in particular, and natural science, but it's still on the outside in economics. And we typically assume bounded rationality. Why? Because when the setup gets more complicated, rationality is not tractable anymore. And so it allows us to go out into that area, and we can model the economy out of equilibrium in two different senses of the word. The idea of bounded rationality comes from Herb Simon, who was already talking about it in the late 50s and early 60s, saying reasoning capabilities are limited. There are many problems we can't solve. We actually solve problems by using heuristics, rules of thumb, myopic reasoning, and so on. And there was a big debate in economics back in the 60s on this point. I'd say Simon lost, and the field went in a different direction. And there's, I think, a key thing to think about is what the wilderness of bounded rationality. So this is building on a phrase originally due to Chris Sims, who said the wilderness of disequilibrium economics. It sort of morphed into the wilderness of bounded rationality. And this, I've heard several economists who are, say, in their 40s or so say, well, when I was a graduate student, I talked to so-and-so, I could name several famous people. I said, I want to build this agent-based model. And they said, if you do that, you'll ruin your career. And the reason was, you'll get lost in the wilderness of bounded rationality. And there's a good point behind that. So in this diagram, in rationality, if you use rational expectations, there's typically only one way to be rational. So it gives you a solid reference point. And the idea is you first do this. Good economists all know that the real world is more complicated, but at least you can anchor things down here. And then you can move into the wilderness, keeping this rationality gate in sight so you know where you're coming from and you don't get lost. I've intentionally put it a bit outside of the wilderness. Now then there's some of us who just reflexively have entered through another equally stylized and perhaps unrealistic gate, which is the zero intelligence gate. I have models where I just assume agents throw darts at dartboards and make decisions at random. And I've actually shown those models can be quite good. If I know things about the order flow in a stock market, I can predict the bid-ask spread by just knowing what the order flow is. So we start simple, and by the way, there's a branch of economics. I'm now momentarily blanking the name of the main guy who's in the business school at Yale, but
Sham Sunder.
yes, thank you. And so you then add some more logic, some more reasoning power, and then you build a model up and you go into the wilderness this way. And somehow the goal is to meet in the middle. I do give one example in the book where we meet in the middle. I don't have time to talk about it here, where we actually have gone from both sides and can actually connect in the middle. And by the way, I think there are many circumstances where rational expectations works pretty well. The example I give in the book is that when I was about 10, we were playing tic-tac-toe in, I think it was 4th grade. And I realized that even if I was going second, I could always at least get a draw. And then my friends all realized it. And then the game became very boring and we quit. So we were able to discover the Nash equilibrium of tic-tac-toe, and that made the game boring. So there are situations where it's a great model, a good behavioral model. Now in agent-based modeling, we do things differently. We model behavior directly with bounded rationality. We could use heuristics. We could assign the agent's goals. So we could say your purpose is to maximize profits if you're a firm, but we give them imperfect learning. By imperfect learning, I mean we give them a learning algorithm. They do the best they can in the complicated situation they're dealing with, and perhaps some imperfect logic. We let them think a few steps ahead, as is in chess, which would be the other example of, at the other side, a complicated game. We don't know if there are any Nash equilibria. Well, there has to be at least one, but there could be a million. We don't know what they are because it's just too complicated. But good chess players use imperfect logic. They use heuristics like control the middle, a queen is better than a rook, and because the goal is fairly far down the road and a bit indirect. We focus on feasible information and allow for non-optimality, model dynamics through simulation in a way that might or might not converge to equilibrium. In a typical agent-based model, let me just see what my next slide is. Yeah. Typical agent-based model, you assign the agents, you give them decision-making roles, information flows in, they make decisions, the decisions have economic consequences. That causes new information because the economic consequences are typically not obvious. So that information flows back. Other new information may flow in if you're dealing with something like a COVID pandemic, and you just go around and around the loop. And you may or may not converge to an equilibrium. You model things from the bottom up. And the core principle I like to follow, I call verisimilitude, which is try to model things as is rather than as if they were something else. The first thing as a modeler I try to do is go, how does this work? How are people actually making decisions in this domain? And I go talk to them and figure out the structure, try and identify what's essential and what you can leave out, make a trial model, discover it doesn't work the way you think, and then you go back and you keep fixing it until it does something that you think is reasonable. Now, I think the field is really in transition. Since Herb Simon's day, computers are 1 billion times more powerful. We have vastly more data, a better understanding of human behavior. Psychology and sociology have made a lot of progress in the intervening time. We have a better understanding of how to build agent-based models from the pioneers that have been sort of off on the edge of the discipline doing this for some time now. And in general, a better understanding of complex systems. And the time is ripe, I think, for this to happen. But until recently, agent-based models have been a qualitative pursuit. You model a generic economy at a generic point in time, and you try and make some conceptual point about the way economies work in general. The problem with that is, I realized early on when I started working here, people can go, well, why should I believe your model? And you can say, well, we match the following qualitative properties of real economies, stylized facts. Okay, fine, but we now have several examples of quantitative ABMs, and I think by making more quantitative ABMs, we can really make this a proper science. So in a quantitative agent-based model, we model a specific economy at a specific point in time. We make quantitative conditional predictions. I want to emphasize conditional predictions because we can put assumptions about policies that are in place in the model or even put in scenarios. There are things like the financial market that's fundamentally pretty hard to predict. And so you might put in that as a condition too. Evaluate policies quantitatively so we can test what they will actually mean in a more tangible way. And I spent a lot of time, sorry, I should have muted my phone. What is the essential, what are the advantages of doing things this way? I could list several, but I think the most essential one is tractability. And in my book, I actually quote Salviego, Bex, and Leibson, and because tractability standard models become intractable as the economic setting gets complicated. Why? Because if you have too many degrees of freedom and you have nonlinearities, it becomes impossible to find the place where agents, the decisions where agents will maximize the utility. You can't solve the equations. And that happens by the time you hit about 10 or so different agents. Okay, depends on the context exactly. In contrast, we use rule-based decision making. It might be driven by a learning algorithm. We can have millions of agents. We can put in as much economic structure as realistically as we want. Now, I should just mention we also recently had an article published in the Journal of Economic Literature. Those of you who are economists will know that's kind of surprising that they let an agent-based modeling paper in there. There hasn't been an agent-based modeling paper in the top 10 journals in economics in 20 years. Top 5 journals in economics in 20 years. But Stephen Durloff actually commissioned the article. And so in this we go into, this is maybe a more appropriate thing for most economists to read. We review the contribution agent-based modeling has made in industrial organization, markets, macro development, public policy, environmental economics, and financial markets, clustered volatility, market impact, systemic risk, and housing markets. And I could, give many examples where I think we've done some pretty solid work. My contributions have been mainly more on the financial side. So if you want, it's a long article, 800 citations, it's pretty exhaustive. It was a bit exhaustive to write too. But anyway, review, and there's a table in there that we agonized a lot about of the sort of canonical neoclassical conception of things. Okay, admittedly, a lot of these are the state-of-the-art and old-fashioned models. And increasingly, economists are trying to get increasing realism over here, for example, by putting in heterogeneous agents into macro models. But typically, in a standard approach, you have to anchor down most of these things, and then you can do one or two of these things at a time. In agent-based modeling, we can do all of these things at a time if we want. It's a virtue, but it's also a danger. There are a lot of agent-based models that generate, unintelligible gobbledygook, or you don't really understand what they're doing. It does require discipline, but and there's now a genre of taking canonical models from the mainstream literature and agentizing them and seeing how they generalize when you put agents in and you allow some of these things to take place. I give a few examples in the book. Now, I'm halfway through. I want to show you a few models. So I'm going to fly through these a bit quickly. We can have some discussion at the end. The first one, when the COVID pandemic broke out, I mobilized my dream team of my best students and postdocs, and we literally worked around the clock to build a model because we saw this was going to have significant economic consequences. And Penny was actually in Australia, so we literally did work around the clock because we'd hand it over to her and then she would hand it back in the morning. And by late April, we produced a model and we made recommendations to the British government about how they should emerge from the lockdown they were in. I happen to have a channel to a guy who, Dominic Cummings, a very peculiar character who was a fan of Santa Fe Institute type modeling. So I had a channel to him. And he was essentially Boris Johnson's Rasputin. So he had a lot to say, even if he was a bit of a crazy guy. So how did this model work? We realized that it was a great opportunity for us because COVID was clearly going to be a very sharp shock that would knock the economy well out of equilibrium, and where we thought a different approach could be really useful. So we predict the effect of COVID on the UK economy industry by industry. We did it under several different scenarios for the emergence from the lockdown, so it was policy relevant. We tested several different lockdown policies. We found a least bad policy, which was to keep the upstream industries open and close the downstream customer-facing industries. We thought it was least bad because there was an economic hit, but it was not nearly as bad as a full lockdown. And there was also More people would die than would die in a full lockdown, but not that many. We actually made a quick and dirty epidemiological model to do that. I think we knew that wasn't our expertise, but I think that is now, people would confirm that. We're very proud because when the dust settled a year later, we finally knew the statistics. By the way, they did take our recommendation. They may have had other reasons for doing it, I can't say. But we predicted a 2020 second quarter GDP loss of 21.5%. The reality a year later, once it was measured, was 22.1%. Of course, you can get lucky. But let me explain how the model works, and I'll then show you a little more about its performance. So here is the British economy at the level of 52 industries. The size of the circles are the gross output of each industry. These lines here are the input-output relationships of the industries. You have the upstream industries like agricultural, fishing, forestry there, manufacturing in the middle, and sort of more consumer stuff at the other end. So it was clear that COVID was going to create shocks because people wouldn't be able to go to work, so there would be a supply shock propagating downstream, and there would be a demand shocks propagating upstream. So our goal was to, first of all, estimate what those shocks were going to be, and then build a model that would tell us how those shocks were going to propagate and interact in the economy. So I'll come back to how we estimated the shocks, but the model was really simple. We said industries can't produce their product if they lack labor, if they lack demand, or if they lack essential inputs. And let me emphasize essential inputs because that was, we did an extensive post-mortem, and it was clearly one of the things we did right was to understand what essential inputs meant. So say take the steel industry. If you look in the steel industry, if you look in the input-output table, okay, there's things you'd expect, and then there's things like iron, coal or coke, and then there's management consultants, restaurants because they have cafeterias. If you used a Leontief production function, not having restaurants would shut down the entire industry. Obviously, that's not going to happen. People can just bring their lunch. So I was on the advisory board of a place called IHS Markit. We got them to do a crash survey of all their industry analysts. So industry by industry, they listed, these are the essential inputs. If you're making steel, these are the things you've got to have to make steel. So we knew what those were, and that turned out to be a major factor. So then we initialized each industry with an inventory. We marched through day by day, and we asked, can this industry produce its output? Does it have labor, demand, and essential inputs? And because we're marching it through day by day, we could watch those shocks propagating through the economy and interacting and getting our result. Now, how did we estimate the shocks? Well, Maria and Penny were both experts on labor. There's this amazing database that the Bureau of Labor Statistics keeps called ONET, and it had nice things like how close together do people in this occupation work? So we knew the map from occupations to industries. We could look and see which industries had workers that needed to work close together. And we said, okay, these guys aren't going to be able to go to work. So we built a pretty good work index, which work could be done remotely. We looked at demand. Anyway, we put the model together and we just ran it, and this is the output we got. So this is the beginning of the first lockdown in the United Kingdom. Time is running this way. Gross output is here, referenced relative to full output at 1. That is the output before the pandemic started. And here we see the predictions of the model industry by industry. Some industries we said they're not going to feel much effect at all. Other industries like this one down here are going to get hit very hard. It's operating at about 35% of its normal output. And you can see there's places where you have jumps and things in here. Why is that? Well, because this industry ran out of essential inputs there, and so its output took a hit. And this black line is the aggregate behavior, and these 3 black dots are measurements of gross output, and you can see we got it pretty close to right, and we even got the time dynamics pretty close to right. This is a scatter plot of the predictions versus the actual things. There's a correlation of 75% or so. We got, if everything was perfect, all of these circles would be along this line. Instead, you can see they're not all in line, but the pattern is pretty clear, and we managed to get things so that the errors averaged out. Since then, we built better models. We teamed up with some epidemiologists. We now have a model for New York City where we really model, district by district in New York City at very fine-grained detail. And every day, the epidemiological model tells the economic model how many people are sick, and information flows back and forth. We now have, back to quantitative models, we now have models that actually are competing head-to-head with DSGs, starting maybe 3 or 4 years ago. These models, I don't want to say they're great, but we're at least able to run tests and look at our predictions relative to those predictions. A lot of room for improvement, an area where we really hope to interact with good macroeconomists who I'm sure know more about macroeconomics than I do. At Oxford, we have our own, we call this a micro-macro model. Why? Because we build things from the bottom up. We take a country, we'll assign the country a couple of million representative agents. We try and build a synthetic population that's demographically matched to the country. We pull a lot of firms out of a database like Orbis and say these are the principal firms, and then the agents work for firms, the firms produce goods. We simulate all the stuff that real economies do. We have a central bank that's setting interest rates, and in the future versions we'll have better versions of financial markets. We have banks lending to companies and businesses. And you can see the model begins by just drawing a map of the economy, thinking about all of the interactions, and then we simulate all these interactions directly. And we showed, we've done it for 38 OECD countries, and we do pretty well. There's a lot of interest in this at central banks now. There's a consortium of 5 central banks working on that. 6 or so central banks that are using a housing model that I don't have time to tell you about that we developed a while ago. No, I couldn't resist putting in a couple of current things. And also because I knew there would be a few economists here, I want to talk about the beverage cycle, the beverage curve, which I think we've made significant progress on. There's a theory that has several Nobel Prizes associated with it about how the beverage curve happens. So what is the beverage curve? The beverage curve is that if you go in and out of recession, I'll show you the next slide. As you go into a recession, you trace out one path. If you plot vacancies against unemployment, you trace a different path as you come out of the recession. And when you go into the recession, the level of unemployment is higher than when you recover from the recession. So the question is, why? And in the standard theory, standard equilibrium theory, they say the workers are reasoning about the firms, and the firms are thinking about the equipment. And kind of a complicated story, so you're at this equilibrium, and then things shift, and you move to another equilibrium, and they write down an equation that looks like this, which says the rate of change of unemployment is the spontaneous rate of separations times 1 minus unemployment, which is essentially the number of, the fraction of workers who are employed, minus some matching function that tells you how workers and firms match up to actually get jobs. Thank you. So in the standard, so the final version didn't get in here. Doesn't matter. In the standard version, you actually set this, let's go back to the previous slide. You set this equation to 0 because you're at equilibrium. You assume that the workers go along these lines where the unemployment doesn't change, and then they go to a new market tightness, and you just set this to 0, solve this. So I meant to have a slide in there showing you what that does. It's not terrible, but you'll see at a glance it misses key features. In contrast, inspired by other agent-based models that we've now built a very simple agent-based model where we assume firms just say that we add a term that was missing in the other equation, which is how many workers are getting fired. In the other equation, you had this term, which is about spontaneous separations, people who leave their job. This term about matching workers. This term is when there's an economic downturn, how many people are going to get fired, and we assume that the rate of change of vacancies is a signal to firms for how many people they should fire. And then the story is very different. Because the story now is an economic downturn happens, firms fire workers, the economy goes out of equilibrium, and workers try to find jobs, so matching happens, but there's typically a delay of around 6 months to a year between unemployment and vacancies, and that's what causes the beverage cycle. It's explicitly a disequilibrium phenomenon, and this red line is our prediction based on this very simple model that we built. So I realize it's probably hard to understand. I'm flying through this really fast, but just to say, at the end of the day, we sometimes can wrestle things down to fairly simple models, and you can now actually go back and ask, is this the right decision for firms to be doing? You can put in rational expectations and test it, which we're doing right now. Anyway, I want to end with another model at the opposite end of the spectrum. This is an agent-based model of energy and power sectors. The agents are real energy and power firms, like ones you read about in the newspaper. We have a 30-year history of all energy generation firms, 95%, and the plants they have at each point in time through history and all the characteristics of those plants. These data sets are not cheap, but we managed to buy them. Each year, each firm may or may not, they decide how much to invest, which assets to invest in. If you're a utility company, do you build a gas-fired turbine or do you build a solar farm? We then look at the new state of the world after the investments are made. We simulate markets. Here we go down to fairly fine-grained, nitty-gritty detail to figure out who supplies how much energy at what price, therefore what revenues, what profits. We estimate the costs. We also have a model of technological progress. We do it year by year, and we can just iterate forward under some set of scenarios about policies.
Along the way, the reader encounters many of Farmer's students and colleagues and learns how research gets done. I kept thinking while reading that this book should be read by PhD students, so if you're in the audience, you should read that book. And that's not only, I should say, because it's always good to question the canon of the discipline in which you are being trained, but also because it offers them students a glimpse into the work that goes into production of knowledge that I think is often hidden or obscured if all you have access to is published research papers. Now, much of complexity economics demands simulations. We just heard parts about it. Unlike standard economic theory, and I use standard following Farmer's language, whose mathematical models are largely deterministic and seeks to optimize the utility of rational agents, complexity economics starts with the assumption that agents have only bounded rationality and is interested in non-deterministic models. Complexity economists like Farmer seeks to understand emergent phenomena that cannot be easily reduced to their elementary parts. Now, Farmer emphasizes throughout the book that the true, and you saw it here today, that the true potential of complexity economics can only be realized now due to the increasing computational power and the availability of enormous amount of data. However, simulations and its impact on the sciences can be traced back to the end of World War II and its aftermath, when first physicists, but after that a host of academics, asked how computers might change scientific practice. Now, historian of science Peter Galison was among the first to question the epistemic status of computer simulation in his 1997 book, Image and Logic. Galison was interested in how physicists use Monte Carlo simulation. Quote, "What are artificial versions of complex processes, these indispensable procedures that are not quite experiment and yet not quite theory?" he asked. So Galison pointed out that simulations trouble the dominant division in physics between theory constructions on the one hand and experimentation on the other. Were simulations a form of experimentation, or is it more accurate to think about them as theories? The question, of course, is just as applicable to the type of economic simulations that Farmer describes. What exactly is the epistemic status of the simulation Farmer and his colleagues produce? Are they experiments? Are they theories? A bit of both? Or something else? In part of the book, Farmer seems to suggest that the simulation is closer to experimentation, writing, for example, and that's a quote from the book, quote, agent-based modeling offers the possibility of creating a digital laboratory where any proposed new policy can be debugged and its effect on inequality understood before it's implemented. Yet at other times, it seems that what is so appealing about complexity economics is that it offers a better theory of the economy. This becomes clear in those moments in the text when Farmer, and we saw a little bit here today, when Farmer contrasts his approach to that of kind of dominant economic theory. As he stresses in the introduction, quote, complexity economics is completely different from standard economic theory. Agent-based modeling, Farmer's claims, offer a better account of how the economy truly functions. As he nicely writes, and you saw it today, we need to replace as-if reasoning with as-is reasoning. A central question for historians of science has been a chicken or egg riddle about empiricism and theory. Which comes first? While positivists and anti-positivists have troubled these questions for decades, I would say most historians of science have settled on what we term theory-laden observation. And that's a way to describe how our theory determine what questions scientists ask, how they design experiment, and what data they consider meaningful and relevant. So this lends me to my first question: how should we think about the simulation produced by complexity economics? And if it is true that agent-based modeling offers a better theory of economic activity, what does that tell us about the nature of explanation espoused by economists? Going back to Cold War physics, Galison, in his book, concludes that while physicists first appealed to simulation as tools for specific calculation, and specifically the hydrogen bomb was the kind of first part, this simulation quickly constituted what he calls, quote unquote, an alternate reality. Indeed, they became physicists' preferred reality. As Galison writes, this is a quote from the book, the computer began as a tool, an object for the manipulation of machines, objects, and equations, but bit by bit, byte by byte, computer designer deconstructed the notion of a tool itself as the computer came to stand not for a tool, but for nature. So I should say that other scholar who studied the rise of simulation similarly noted that over time, computer simulations replace or usurped that which they purported to study. And here I'm thinking about other scholars like anthropologist Stefan Helmreich. So will the same be true for complexity economics? Will the meaning of the economy as an object of inquiry be refashioned into whatever can be simulated on computers? And what might be the implication of this change? Now, I think here of the work of Donald Mackenzie, who has argued that at least as far as finance is concerned, the emergence of economic theories of the financial market, quote, did more than analyze markets, it altered them. A claim nicely captured in the title of his book, saying that these models are an engine, not a camera. So even though his argument that even though this model started to as a camera of the market, a way of capturing something true about the market, they became an engine that became changing the market and determining how the market actually functioned. So can the same be said of agent-based modeling in financial markets? So this question regarding methodology speaks directly to the disciplinary conundrum raised by Farmer. Complexity economists, Farmer writes, are a fringe group, potentially changing a little bit, but still a fringe group. Whereas some of their models have now been adopted by policy bodies and banks. As far as the academic discipline of economics is concerned, the work is suspect. Why? So one answer might be that their approach simply questions some of the most basic tenets that have dominated the economic professions for decades. So I already mentioned the rejection of perfectly rational actors factors, but another premise, for example, is economist assumption that supply and demand are in a state of equilibrium. We just saw an example of that. As Farmer writes in the book, for complexity economics to make it into the mainstream, quote, a complete makeover of tools, skills, and knowledge base is necessary. Now, Farmer described this as a cultural sea change, although I think that an epistemic sea change would be a more appropriate descriptor than a cultural one. Complexity theory's growth in the second half of the 20th century represented, according to historian of science Norton Weiss, an invasion of the hierarchy of the natural sciences, putting biology rather than physics at the top. With this inversion, the emphasis shifted from analysis to synthesis. The ultimate goal of explanation or understanding was no longer trying to reduce phenomena from higher order organization to lower level elements, but rather focusing on how elementary objects get ramified into complex ones. So economists might be more resistant to this inversion in its concomitant alteration of the meaning of theory, but I suspect that more is at play. What distinguished complexity theory from the beginning was that it posed a challenge to traditional disciplines, so be they ecology, meteorology, or finance. In a sense, complexity theory proposes that there are deep commonalities shared across these other fields, and that researchers' attention should be trained towards these commonalities rather than what is unique to any discipline. So it is easy to see why this sensibility is an affront to most scientists. Academic disciplines are centered on object of inquiry, on concerns. A biologist is an expert on living things, and a geologist, claim to knowledge, is her deep understanding of the planetary rock record. How could a physicist or a mathematician claim to know more than a biologist or an economist about their own area of study, whether life or the economy? Now, Farmer argues that complexity theory is useful since the economy and ecology are analogous to each other. Now, I do not doubt that one can draw parallels between the two, and that doing so can be illuminating. However, it's worth noting that ecology, as a modern discipline, emerged in the 20th century when ecologists defined their object of study not as the environment, but as ecosystem, a complex system that could be measured, modeled, mathematized, and predicted. And this is following the work of historian Sharon Kingsland. If this sounds curiously like the origin story of economics, that's because it is. As such, it's not so much that ecology and economy are analogous, but rather that having already applied complexity thinking to ecology, scholars now seek to do the same to economics. Now, complexity theory's direct challenge to traditional disciplines might explain, at least in part, why the field has flourished in places such as the Santa Fe Institute, where the social organization and the intellectual projects enable one another. This explanation must have some merit, but it still does not explain why economists or economics seems to be especially resistant to complexity theory. So when I first began reading the book, I feel like I need to confess that I was somewhat surprised. So I assumed that by now the battles between complexity theorists and other disciplinarians were over. I didn't realize that it is still a live debate in economics. So why has there been such a resistance to the idea that Farmer and his colleagues are proposing? One clue might be found in a recent book by economic historian Jonathan Levy, a book called The Real Economy, A History and Theory, which was just published last month. Levy argues that economics, as it developed in the decades after World War II, was defined by method rather than a subject matter. As Levy writes in a recent publication, quote, "To state the point most provocatively, economics has no subject." The elevation of method over subject, according to Levy, was an outcome of the rise of marginalist value economics. In the post-war period, economists focused their attention on reasoning through mathematical models, which came to stand for the real economy, these models. They focus on method, Levy writes, this focus on method, Levy writes, also explained the influence of economic theory across multiple academic fields, from law to political theory. And I would add here that this proliferation of economic theory was enabled not simply by a focus on method, but on a specific method, which in my own work I term axiomatic thinking. Now, the reason I'm mentioning Levy's recent work here is because if its diagnosis is correct, it might explain the resistance to complexity economics among mainstream economists. Farmer and his colleagues do not seek to just add another technique to economists' toolkit, but rather to dismantle the discipline as we have known it since World War II. Now, Levy is not the only historian to point to the constructed and limited meaning of the economy as an object of study, although he does, I should say, in the book, seeks to offer a positive definition and not just limit himself to critique. Historian Timothy Mitchell here at Columbia and Timothy Shank and sociologist Daniel Hirsham have all written about how the economy emerged in the 1930s as a discursive concept, which allowed people for the first time, for example, to talk about the economy as growing as the economy as shrinking. So as these scholars have shown, before the concept of the economy dominated the discipline of economics, the social and the economic world were much more closely linked to one another. Indeed, economics was taken to be a branch of sociology, and much more emphasis was placed on society. As Timothy Mitchell writes, quote, "The economy came into being between the 1930s and the 1950s as the field of operation for new powers of planning, regulation, statistical enumeration, and representations. Though these novel forms of political rationality and practice, it became possible to image the economy as a self-contained sphere, distinct from the social, the cultural, and other spheres." End quote. So as Mitchell further explains, creating the economy necessarily entails delineating all that exists outside of the economy. And what is remarkable from a historical perspective is how quickly the concept of economy figured in political discourse as well, how quickly it became an object for politics. I find these historians helpful as it not only reminds us how relatively recent is the standard view of economics that complexity economists wish to unset, but it is also does not have to necessarily be so. Looking to the future rather than to the past, this work raises a host of questions. If Farmer and his colleagues in the field of complexity economics succeed in their endeavor, if they convince their colleagues to question some of the fundamental dogmas of their field, should not this potential moment of reckoning be used to think even more capaciously about what the economy is? How should the social figure in this reconceptualization of the economy? And how should we reckon with the realization that regardless of how economists choose to answer these questions, the economy will continue to be an object for politics? Thank you.
So I've really enjoyed getting to read this book. I actually knew a certain amount about what Doyne had been doing. I've been an admirer of his work for a long time, but it was great to see the amount of progress he's made. And I guess I should also say, even more than admiring his ideas, although I think there are a lot of interesting aspects to them, I've been and continue to be a tremendous admirer of his courage in, taking on something that nobody else told him he was allowed to do. But I think he's taken it very seriously, and that's something I hope all of you will take inspiration from. I think, certainly the students in economics here, I would also encourage very much to read the book and even more the Journal of Economic Literature survey that takes a lot of the discussion even sort of deeper into applications for economics. And I think there are a number of important reasons why economists should be interested in what the agent-based modeling program can help them to do. One reason why I think, he's not pushing against complete resistance from current trends in the subject is that I think it's obvious that ever cheaper computing power is going to make it natural for economists to make much more use of computational methods. That idea that we now have a tool that lets us do new kinds of things and we need to make much more use of it is obvious. I think it's already happening in a lot of ways. In our PhD program here, we have more than once in the last few years had visitors come in to give mini courses or even a full semester-length course on computational methods, and I think we should be doing much more of that, because I'm sure the research of the coming decade and further will be increasingly using those tools. Another aspect of the program that obviously economics needs, and I think is going to necessarily become much more like, I think there's a clear reason to think it's desirable to take into account much finer-grained heterogeneity in the way economists are interested in modeling both markets and entire economies. This is something that is increasingly being pursued even also in mainstream macroeconomics, and Doyne mentioned that as, I guess, an example of a case where the mainstream is willing to use some element in the other column. I think macro modeling that introduces many kinds of heterogeneity and appeals a lot more to individual level data on individual households, individual firms, as well as finely differentiated sectors and regions and so on, is very much something that's been happening for the past quarter century at least. For obvious reasons, it relates to the greater availability of individual data, which is much more possible now, and also cheaper computing power, which makes it possible to answer questions taking into account both much more data and having models with many more variables in them. There's another reason why I think the program is doing something that represents where economics has to go, is one that is maybe not as much already embraced by the mainstream of the field, but is one where I think the field needs to go, is I agree with Doyne that it's important to be able to model processes of adaptation of people's behavior to their environment rather than simply assuming equilibrium. And I think that there is a problem with what we teach too much of is the degree of focus on simply defining and analyzing equilibria. I don't think that the alternative represents simply abandoning everything that is taught in economics and starting from a completely different place. I think the concept of equilibrium has actually been a very powerful and useful concept that people should understand how to work with. But I think that we need to understand it as a possible limit point of an equilibrating process rather than thinking that the whole theoretical structure of the field is in place if you can just define what an equilibrium situation would be and know how to study the properties of such a thing if you reached it. Why do we need to think about equilibrating processes as one does in the kind of models that Doyne is talking about? I mean, one simple reason is many models, and we're very familiar with this, when we define equilibrium, we find that there can be many equilibria, and then so there's the question of equilibrium selection. If you're trying to make a prediction about what should happen, modeling the process of equilibration may well lead you to conclude that some things that would be equilibria in principle should be unstable under that adjustment process and then unlikely to be reached. Other ones might be stable, and so you should be more interested in those as possible outcomes. You could try to define basins of attraction for different equilibria and so on. And I think that's all very important as an additional understanding of how to think about the models and their relevant predictions. I think it's very important for us to understand the issue of speed of convergence, even when we think there should be eventually convergence to an equilibrium. I think that when we think about analyzing desirable policies, thinking about the desirability of creating an environment where you would expect faster convergence to a desirable equilibrium, and not simply being content with saying that if you could get to the equilibrium, it would be a good one, is from a practical point of view often a very important issue. And so even if you're convinced that in the models you're interested in there should be a single equilibrium and you should surely eventually reach it, the fact that under different ways of designing the environment that you could expect faster or slower convergence is actually a very big and practical issue. Of course, models, realistic models of equilibrating processes might converge or not. And that question, I think, is also something that is often going to be important for policy design. You might be interested in creating environments where you would expect convergence to equilibrium, as opposed to creating an environment where you have a reason to think that that it's not going to happen. That's been something that I've been interested in as a ground for choosing between monetary policy rules. I think that, at least in the kind of models I've studied, rules that I would regard as desirable imply that there should be relatively fast convergence of plausible seeming equilibrating processes to something like a rational expectations equilibrium, but other policy rules definitely would not imply convergence, and I think that would be a reason not for recommending those policies. If you simply assume you must be at an equilibrium, you would not you would not appreciate that concern. And finally, I think economists should clearly be interested in at least some phenomena where the fact of not being in equilibrium, or even having dynamics that are tending toward an equilibrium, is completely crucial for understanding the phenomena. Maybe my favorite example would be understanding hyperinflations. I think that these are examples of phenomena where you can't really understand what's going on. And the characteristic feature is not that you have high inflation, but that you observe that when the thing happens that leads the experience to be classified as a hyperinflation, you see it spiraling out of control to higher and higher and higher inflation until something has to change to stop the process. And I think that the right way to understand what's happening is that people are trying to adjust their behavior to changes in their perceived environment, but as they adjust their behavior, they make the environment change even more, which requires them to adjust even more, and so on, in a process that spirals farther and farther from anything like an equilibrium, as opposed to one that's converging to an equilibrium. Okay, so there are a lot of reasons why I think it's going to be important for all of us to learn to do models more in this spirit. I do think the book nonetheless oversells what has already been accomplished by the ABM paradigm, and I guess partly this may be the fact that it was written for a relatively popular audience, not for me. But anyway, it was not in all respects written for me, because it does, I think, in some ways make things seem too simple. So one respect in which I would say that is I think the book downplays the extent to which it's been an obstacle to broader acceptance of this approach to economics, that it's difficult to make the findings from numerical simulations replicable and interpretable. So I don't think it's so much that there is some kind of methodological orthodoxy, which means the editors of the top economics journals simply will not consider this kind of work because it's violating some orthodoxy that they think it's their job to enforce. I think it's this issue of the editors and referees having trouble being sure about the replicability and interpretability of simulation results that's the obstacle. And in saying this, I mean, I'm not saying so therefore don't anyone waste your time learning how to do it. But I think people like Doyne, who are trying to push the program forward, need to take seriously the extent to which this is one of the big challenges that they have to face. If you ask why the field of economics was as attached as it was to this traditional method of theorem and proof and the kind of beautiful papers people would publish, I think it has a lot to do with the fact that that was convenient for cumulative growth of knowledge, because once you did the proof, you could explain it all on the page to people, and they could check it and convince themselves that they really understand how your assumptions lead to your conclusions. And that didn't mean that then they have to say, okay, the world is like that. It's a true theorem, therefore it's the only way to think about the world. But it did mean that they knew what they had learned from going through the derivation, and then they could criticize it. It's not that they could try to build on it by varying assumptions. They could say, well, now I see, why assumption 2 is something I really don't believe. Because, it seemed kind of plausible when you stated it. I thought, yeah, plausible enough, convenient simplification to let the derivation go forward. But when I see how the reasoning goes, I realize assumption 2 is really, really strong once I see how it works in the context of the analysis. And so now I realize I must not at all sign on to assumption 2, but here's my idea, assumption 2 prime. Let's see, how the analysis would go with that instead. And so you can make progress in the discussion of assumptions being attractive or not when you proceed that way. And the problem, I think, with the simulations is that people can report a particular simulation, produce numbers, but people often have doubts about, am I sure what I know then? Even with that code, if I set it up with different initial conditions, would it really produce something that looks like that? If I tweaked any of a very large number of parameters in the code, am I sure it would continue to produce things like that? And these are the questions that people doing the research need to figure out how to communicate to the rest of the profession in order for the work to be having the impact that, again, I hope it will have. I mean, I'm not in any way saying, so it's a wrong method. I'm saying there is a challenge to figure out how to explain to people what you're learning. Another thing that I think the book is content with greater simplification than I would want is, I think it seems to be celebrating a style of agent-based modeling in which the agents are very simple, but the structure through which they interact can be quite complex. Some, elaborate network structure and many parameters and how you specify the environment in which they interact, and the agents themselves are doing very simple things. So their decisions aren't affected by any complex history of their prior experience. They're not based on a model of the world that the agent has that they use to project possible futures associated with their different actions. It's some, very simple stimulus response kind of rule, responding to only a few aspects of their local situation at that point in time. And, I would agree that, of course, many traditional models go too far in assuming a perfectly rational decision maker who not only has a model of the world, but one that is fully as complex as the reality of the world. Their model of the world is exactly the right one, or at least coincides with the modeler's model of the world. And, that, I think, is also extreme. But the models in this literature that's being described are often ones that assume no ability to look for patterns at all, or no ability to learn from experience, which I think is missing something important. And it has an important consequence for some of the work that was not discussed in Doyne's talk here, but that there's a lot of space on in the book, which is there's a lot of emphasis in the book on the possibility of repetitive cycles and chaotic dynamics as things that result from mechanically following simple heuristics. And that's something that, of course, has been known in the economics literature for more than a century. In particular, the famous cobweb model of agricultural cycles was introduced back in the 1920s. And but there was an important critique of that kind of modeling that came in with John Muth in 1961, arguing that the classic cobweb cycle, which assumed you got cycles out of assuming that producers would respond to high prices by producing more, but then sending a lot of stuff to the market and resulting in low prices the next season, which led them to produce less, which then resulted in a shortage of supply and high prices the next season, and so on. And you could easily show you get endogenously a repetitive cycle. But what Muth pointed out is that implies that producers are in fact basing their decisions on anticipations. They're changing what they do from year to year. They're responding to anticipations that are always exactly wrong. They're always expecting a high price exactly when it's completely predictable that the price will be lower than average, and expecting a low price exactly when it's predictable that it's higher than average. And so the model was in fact relying on not noticing a pattern that was itself pretty simple. And I think that for people to be interested in, say, endogenous cycle models, you want to think that the endogenous cycle model doesn't depend on people being completely unable to recognize patterns, even when they're simple. A third thing, I think I'm almost out of time, probably. Is that, or am I, yeah, okay. I think there is too much emphasis in the book on simulation of completely deterministic models as opposed to models that are subject to random shocks from outside the system, and then asking how people try to adjust to those unexpected events. I don't think it's true that random shocks have the role they do in mainstream, say, macroeconomic modeling, only because we think the economy is a system that would have to converge to a steady state without these random shocks. Therefore, we postulate random shocks, even if we don't know what they are. I mean, I think it's because we often see them. You know, we see sometimes a madman is in the White House and decides to just, impose large tariffs of all kinds in different parts of the world, and the day before, few people, were predicting it. They didn't quite know that was what was coming, and we're not entirely sure what the logic is even after they've come. And so people are all scrambling to adjust to something that, was not something they knew was coming or had assigned a probability to or anything. And I think that a lot of what does matter to the macroeconomy is responses to things like this. I don't think we should assume, of course, that the way the system responds to these things is an equilibrium, that it's part of a stochastic equilibrium that you've always been in and you continue to be in as the random things occur. But I think that the reason we need to go beyond equilibrium modeling is not because the asymptotic dynamics of the economy are chaotic and they never converge, and that's why equilibrium modeling isn't in fact the right answer. I think it's because these asymptotic dynamics are largely irrelevant because more random things keep happening. And so what matters a lot for what you see in the economy are the relatively short-run transitory responses to random things that have happened. And for that, asking how people try to adjust to surprising things that happen to them is the key. Studying whether asymptotically dynamics would be chaotic or not if you push the dynamics forward for centuries with no random things ever perturbing the economy in the meantime is not so much the issue that we need to study. Thanks.
You want to take a few minutes and respond?
Oh, yeah.
We'll open it up.
Thank you. Well, first of all, I want to thank both of the discussants for their thoughtful remarks. I was very pleasantly surprised by Mike's positive view of what I've been doing. And so I'm really happy with that. And I don't really disagree with any of the critiques you've made either. Maybe some subtle differences. So basically four things. I just didn't have space to talk about how does one make an agent-based model interpretable and replicable. And it's an art. You have to set that up in the way you do it. It's like, if you're in a lab, you have to learn how to keep all your equipment clean and make sure that everything's done properly and you record things the right way. So it's the same thing here. It's something that doesn't just happen automatically. And so I think of it as you need to build in lots and lots of stethoscopes so you can see what everything is doing. And then you need, at the end of the day, to understand why it's doing what it's doing. You have to build the model so it's plug and play, so you can quickly mess around with it and go, oh, wait a minute, when I pull this out, this seems to be the key thing. And I have an example in the book where we started with a fairly complicated model of the banking system with multiple banks and a primitive model of the real economy and a bunch of stuff. And we imposed the value at risk Basel II risk management rule on it, and the whole economy starts to oscillate. And we went, wow, what's happening? And to figure it out, we just kept simplifying until we got the essence, and then we were able to write down a very simple stylized model. And actually this model I just gave of the beverage curve is another example where we've been playing with a much more complex model of occupational labor diffusion for years. And then I suddenly realized, my gosh, we could just make this much simpler model and explain it quantitatively in a very crisp way. So, but this is a challenge. It's not easy to do. And it's something where you have to train people, you have to put in the right protocols and really work hard to do it. But, and many people haven't. And there are a lot of agent-based models out there where I go, come on, okay. Point 2, agents are too simple. I completely agree. This I view as just the stage we're at. In my picture of going into the wilderness, we're not as far in there as I would like yet. And I think we need to take a step at a time to make sure that we understand what the system does. I could have told a story about understanding market impact in financial markets. You buy something, you move the price. It happens in a very particular way. And so we started, I mentioned this in my talk, with a model that literally assumed agents just placed orders at random, somewhere around the current bid offer price, but they just threw them in there at random. And we were able to explain some things, but not others. And then more sophistication had to be added. But we really want to get more behaviorally realistic. What we would really like is to be able to talk to a behavioral economist and say, okay, tell us how this agent should be behaving. We put that in the model, and then we see what the economic consequences are. So that's where we want to head. We just aren't there yet. We need a bigger effort. We need more resources. We need more time to get there, but completely agree with that. And I could show a few examples where that's starting to happen. It's helped along by the fact that machine learning's made big steps. Reinforcement learning is now much more turnkey than it used to be. Okay, I think we agree. Mechanical, 2 simple agents producing dynamics. I agree with that, but I want to, sometimes when I give this talk, I was looking around for a pole. I do a demonstration of pole balancing. And so you take a pole, it has to be at least about 3 feet long. You try and hold it vertically upright. Now, when you do that, and if it's a real person who's an imperfect pole balancer, the pole spontaneously oscillates. Why? Because the person is looking ahead. You have forward-looking logic, but you're just not perfect at it. And because you're not perfect at it, you undershoot, you overshoot, and the pole wobbles. Now, a caricature of a DSG modeler might be that the DSG modeler says, no, it's a perfect pole balancer, but its shocks are hitting the hand of the pole balancer. And they are different, because in the first case, it's exogenous, and the exogenous cycles are really coming because of the imperfections of the pole balancer. But I completely agree that a lot of the time it's outside shocks. Our COVID model was a shock model. And it's just a question of getting that balance right. I think means if I pushed hard on deterministic oscillations, it's because I think that's missing in a lot of contemporary macro, or most of it, even though it existed in an earlier phase of macro. And certainly I agree that, models are, the real economy, we're going to have stochastic and deterministic models. So I almost agreed with everything you said. Thank you. Alma, I don't know how to respond to what you said exactly. I agreed with many things you said. I'm actually maybe less antagonistic about mainstream than you might have indicated. I worked very hard in the book to be as nice as I could be. Whenever I headed to an economist and they would say, look, you're being too mean there, I would just throw it out. So so I don't know if I achieved that. I did have to say a few critical things. But, and I do think in the future, I'm not saying to toss out, actually I had a couple of notes here. I'm not saying to toss out the whole thing, because do think there's a lot of places where, the kind of methods of reasoning and calculating equilibrium and so on can be really useful, particularly in simple situations, simple examples where an agent-based model would be overkill and wouldn't have the advantages that you're pointing out of interpretability and so forth and understanding. But I do think that the thing I really want is just for the mainstream to open up and let some of what we do in. And, let some papers into the top journals, hire some people at universities and economics departments. My graduate students are brilliant. They're doing what I consider to be really good economics. I think they deserve to be at, the best places. And so that's my only ask, really, is just open the window a little bit. And you were very supportive, so I appreciate that.
Okay, I'm going to open it up, but I'm going to abuse my position and start with and maybe start with a question, then we'll take a round to anyone. So I was sort of curious, partly because it's actually riffs on what Alma was saying, which is that economics is not just about making predictions about the behavior of economic data. We're also telling narratives about what society is, what society should be. We're having the standpoint that there's this policy-making audience that we're communicating to that then somehow is going to do some things to this economy thing. And then that's going to stay stable. And what, I think part of the points of one reason modern macroeconomics looks the way it does is because of the experience of Keynesianism in the 1970s, where it was sort of thought that we weren't capturing what was actually stable and what was transitory, and so we had a misstated model because we were kind of trying to do too much curve fitting through the data, and we didn't have good what we'd call structural models of the economy. I'm not saying we do have great structural models of the economy, but that's kind of the hunt and why we're a little bit, I think, resistant to, on one hand, we're resistant to sort of elaborate curve fitting in some ways because we want to make sure that we have the things that we think will remain invariant to a policy decision. But then I think that's on the scientific side of things. But then I think there's this other more political theology side of what economics is, which is it's also just kind of doing a whole bunch of folk narrative in how society works. And one of the delicate things in economics is that we're kind of this witchcraft brew of both this predictive science and this political theology. And so I think, Doyne, you're kind of going after us only on this, but not understanding that we also are optimizing on this other sort of thing that's kind of a function that's demanded of the disciple.
Well, I don't understand that.
Yeah.
I certainly understand.
And so that's my comment, but I'll take it. You want to respond? Yeah.
Yeah. I mean, yes, policy is the main thing. Now, policy, I would argue, is still about prediction. Because what are you saying? You're saying, we adopt this new policy, what will happen? We adopt policies because we think something's going to get better, but it's about cause effect and it's about conditional predictions. But in order to have some faith that when we adopt a policy, which typically take us into a place we haven't been before, all the more that we ought to be starting with a model that can at least do some reliable prediction for the world as it is, because otherwise, what reason do we have to believe the predictions will be there? I actually think policy is a big strength of ABM, because taken climate, most of the economics work has been about carbon taxes. Carbon taxes are politically unpalatable and very hard to implement and tricky because, do you have a carbon market? How do you get the right price? There's been a lot of failures so far. It has not been effective. But so the policies that have been effective are things that are much harder to put into traditional models. They're easy to put into ABMs. So I actually think we can make policy analysis better. I think that's a strength because we can put complicated brute policy, portfolios if we need to. And yeah, so but I totally agree that that's why economics is so important, because it actually can help us make the world better. And we've got to understand what can we do to make it better?
Should I respond to it?
Yeah, you could go for it.
I also agree that wanting to have models that can predict is in fact very important to what economists are trying to be able to do, because that is often an input into the policy process that people are interested in having economists on their staff exactly for. But I think also in that process, the issue of interpretability of the model is actually a big deal.
Oh, of course.
Because
Yeah.
what happens in practice is having an economist who comes in and says, I have a big computer and here's the number that comes out, has pretty much no effect on the policy, because the policymakers want to know, where did it come from, and which assumptions are you making that I would not necessarily make. And so they need to have a discussion with this person about what does it mean, what's the story basically that the model is telling that it comes out that way. And what is at least not uncommon is that in policy institutions, smaller and less complicated models actually end up being used more in the policy process than the ones that have also been developed in-house in the spirit of trying to bring as much of the real complexity of the world in, exactly, I think, because of this issue. Because, of course, there's a obvious virtue of saying, I want to try to make it as close to reality as possible because I want the numbers to be ones I think are right. But there is this other side of not just you personally produce numbers that you personally think those are the assumptions you would have made, when you have to explain it to the people who are going to actually take the policy decision and have to stand behind, get shot at for whatever they did or didn't do. They are going to want to feel that they understand something about where the number came from in order to actually use it. And so I think this is not a non-issue.
No, not at all. And I should have said the word narrative. I think at the end of the day, you have to understand what your model's doing and have a narrative that you can explain. It's this, or maybe it's this and that, but you have to have a clear story. And it can be more difficult than it is when you have a simple set of equations, for sure.
We'll start at the back over there.
First, I'll preface my question and comment with the fact that, for those of us who have been trying to flush the grouse out of the brush for the past 30 years and doing complexity and dynamics and things like that in finance and other fields, kudos for articulating the science of that relatively succinctly. And I think you've done a unique job at that. And from there, I think there's some of the challenges that we face in this is this whole concept of verisimilitude. There's a lot of onus on the analyst's skill in the behavioral economic sense, or just the behavioral sense, to characterize what each agent or the heterogeneity or representative strategy sets and behavioral sets of those agents should be to even get the simulation to work. And then even worse, there's the problem that in economics, I think most of our systems are heavily dominated by noise. And noise has color and needs to be statistically interpreted with some form of information or entropy. And even if you were to do that, you don't get any really conclusive results out of it. So I'm just wondering if you've encountered or have any advice in the practical side of running these simulations is how do you actually validate verisimilitude as like a econophysicist who would trust the data, let the data speak to you before you make a hypothesis. But here you still have to posit up front, and that puts a big burden on your hypothesis and thus the results of what comes out of the system.
We'll take a couple and then over here.
Yeah, thank you. If I understood correctly, your case for ABMs was partly that because of this sort of chaotic aggregation from the microstate to the macrostate, you better model a lot of aspects of the microstate, and ABMs allow you to do this at low cost. But then you also suggested that this is not monotone and there must be ways to discipline yourself because it's kind of become too easy to add more and more things that are not always useful. Are there formal ways to think about it, like ordering assumptions so that you can include them in order of importance, maybe bundling them so that it makes sense to add them together? And maybe on a related note, and what you talked about earlier regarding prediction and explanation, it seems that the consequence of sort of like chaos theory is that the intelligibility of a mechanism is not a feature of the model, it's a feature of the world. And if you look at your chaotic model until you have like a simple narrative, wouldn't that mean that you could break it down again to something more in the realm of mainstream economics? Isn't the realm of chaos kind of saying the mechanisms aren't intelligible?
Thank you. I guess it connects to Chris's question. We talked about, one example that came up is DSGE models, and when I think about that, there's a lot of cumulative knowledge going into that. Like when I calibrate that, I know that these parameters are common in the literature and I can just take them. And I'm really interested in what, sort of if this ABM literature goes mainstream, what cumulative knowledge would look like. Because to me, I haven't worked with them, it seems like you don't really plug in parameters, but it's a way of calibrating how people interact with each other. So it would be fascinating to hear your vision of how that would look like if people build on each other. Like, would it just be like a big GitHub repo where people upload their models that seem to have worked?
We can respond and then we'll. Go ahead.
Okay. First question about validation. Really important. Parsimony is really important. And, what we try and do, and we did this when I was at Prediction Company, take the data, divide it into 3 parts. Use a third of the data to train the model. Test the model on the second third, and only when you're pretty confident that you're doing something really good, you do a final test on the other third. And then you can retrain the whole model on everything. But out of sample is really vital. And if I made one criticism of econometrics, that's not done often enough and carefully enough. And my role as a mentor is usually to beat statistical significance out of sample, overfitting, to get my students not to do those things. It's very hard because as people, we overfit instinctively. And so it's true though, what you said, there's a lot of art in this. It's not something that's easily reduced to a cookbook rote procedure yet. But, so now there was a question about chaos. Oh, and does it mean not intelligible? So I don't think so. I give an example in the book of a model, I already mentioned it in the discussion, where we boiled it down to there's a bank and a value investor, and the bank is using leverage, and show that the system's chaotic, and it produces something that looks like the Great Moderation for about 10 or 15 years. The market steadily climbs and then it crashes, and then it does it again in a chaotic way. But chaos is it's a bit of a misleading word. It's an example of, Jim York, who coined that word wanting something catchy. So he used the word, and it's catchy. So I'm sure it helped the field, but it causes people to think it's some miasmic state of confusion that it's not. In fact, it can actually be used to make better predictions. One of my most cited papers is called Predicting Chaotic Time Series, and we point out we actually could beat traditional time series methods by using nonlinear methods that took advantage of chaos. Cumulative knowledge, it's a really good question. We're in a funny place right now because we've been approached by literally 5 different groups, little groups within 5 different central banks about macro model. Everybody's been building their own models. Seems better to create a platform like Doyne, for those of you who are familiar with DSGE, where we can just test things it's easy to create new things. There's lots of tests built in. You can benchmark everything against everything else. This has been used to great advantage in machine learning, where you have benchmark problems and you score every model against the benchmark problems. And that's what we need to do. And that's, I think, the only way we're going to get a sensible accumulation of knowledge. It does require some cooperation across groups, creating frameworks that are, it's harder to create this framework than Doyne. but it's a important challenge to do. Thanks. Good questions.
Hi, I have two questions. The first one for Professor Farmer. So in the book, you talk about sometimes how people sell their houses, like the heuristics they use. And I'm wondering for if we ask a model for a policy recommendation, say, the behavioral assumptions should be invariant to the policy. It sounds to me that rational expectations, like trivially, are invariant, right? So how can you make sure that the heuristics are going to be? Yeah. And the second question, sorry, for Professors Woodford and Steingart. It sounds that the climate science is already a precedent for simulation in science. So can that be also an example for peer review, as it was mentioned in the discussion?
We'll go over there.
This is a question for Professor Farmer. You said agent-based models have been able to produce more fruitful results or effective policies for like climate change, and I was just wondering, what are the insights that ABM could offer for a collective action problem like climate change that are pretty difficult to tackle for traditional, I guess, carbon policies, as you've pointed out.
Yeah, so as you were describing the approach to ABMs, I was thinking about the Lucas critique, right? So overall, how are you addressing that in terms of parameters, hyperparameters?
Great, go ahead.
Okay, so I think the first and third questions are very similar. And it's a challenge. I really believe in, Lucas critique is, yes, that's an important thing to worry about. And there's two ways to deal with it. One is to base the model around behaviors that you think are pretty invariant. I think, financial investors are always going to want to buy undervalued assets. So that's pretty invariant. Firms want to make profits. But that's giving them a goal. But it's just so one needs to look at what's invariant, what's not going to change. And now, this has been done in some very stylized papers, but has not been done well yet. To use the same approach that was used in AlphaGo, for those of you who are familiar with that, where you basically got machine learning algorithms to play against each other to play Go. And there you evolve very smart players. You can do this in an ABM. You take the firms and you have them compete against each other, and you give them reinforcement learning algorithms, and you try and train firms that are good at setting prices or good at deciding how much to produce based on the information they have, and so on. Now, then when there's a policy change, you've got to retrain those firms and see how they adapt. And then you can probably, assume that when the policy change happens, they'll figure it out and they'll go to that new way of behaving. So that's where the field is heading. As I said, it's been done in 2 or 3 papers, very, very, very toy models of the economy. So we're not really there yet, but I think we're going to be there in another year or two. Now, there was a question, have ABMs produced more effective policies for climate change? So far, I would say not really. That has not been where the effort's been. I do think the model that we're developing that I mentioned, our goal, quite frankly, there is to really displace integrated assessment models, which have not done a very good job. And I think we can just do a better job. But is it easy? No. That's why we have a company. Actually, one of the lead guys is sitting back there right now, and together with the project manager who keeps them on track. And, we need a big team. This is not this kind of model where we're literally simulating the entire energy system That's a big project. Huge amounts of embedded domain knowledge, which is one reason I think it will work, but it also means it's a lot of work because we aren't just making a stylized model of the economy. We're putting in a lot of nitty-gritty stuff about the way the technologies work and about the way firms decide and the financing happens and so forth. But so far on climate change, where I've contributed has been looking at the history of technological transitions, not really complexity economics per se, in a sense just econometrics with an awful lot of data collection and thinking about what technologies actually do. But we're embedding that in this bigger model that I think we will really have something. I hope within 6 months we'll already be there.
If I should answer the question about climate modeling and whether that proves that simulation, the simulation approaches or shows us at least how to do it in economics. I mean, I think there are important differences that make it easier for it to be successful with climate modeling. And what I would be inclined to say is that that's an example of a system where what you ought to assume happens locally in each little cell of the atmosphere, you have a lot of basis for specifying it in a particular way. The basic physics is well understood. And there are also good reasons for thinking that the relevant causal effects are very local, because it's not true that this little cell of the atmosphere is being affected in some complex way by the history of things that have happened there or elsewhere in the atmosphere. I mean, the simple physics does imply that it evolves from what it just was right before, and insofar it's impinged by other things, there are the other parts of the atmosphere right next to it that are impinging on it, and so all of that structure is well understood as the only sensible way of setting up the model, whereas there is something that's hard, which is tracing out then the global effects of, how do something like a hurricane or something work through the interaction of local things happening in a bunch of different places, and tracing out the complicated chains of causation that occur as you run it forward. The computational model, of course, can help you think through that hard problem very well, but the pieces that you want to put into it, you can be pretty sure you're setting it up the right way. And I think in the case of modeling economic behavior, there's much more reason to doubt that, very simple rules for what the individual, if you think of households or firms as atoms, or, even little pieces of the atmosphere, I mean, there's much more reason to at least be worried that they might be complicated in what they do. Case of economics.
I mean, I'll just add like a small thing about the climate science simulation, which is, I absolutely agree that the physics there makes a big difference, but there's also this question, which is the climate science simulation the simulation themselves don't have themselves impact the climate, where here we have the case where the economy, the simulation themselves potentially act on the economy, so it does complicate it even more.
I think that kind of takes us to, okay, we'll have one more question. And then, yeah.
Not sure it's a good enough question to deserve its status as the last one. I just wanted to stress the difference between the interpretability of the results that Mike talked about a lot, and the art and discipline that goes into constructing the model that Doyne talked about a lot. Because I think the interpretability is crucial, in my opinion. The art is extremely important, but there is a lot of art in how we write models in mainstream economics. We might fool ourselves saying, no, we check all the assumptions, etc. Of course we don't. We write a model and either we follow the fashion or we have thought about it ourselves and we have a sense this is a good depiction, but there is art just as much. So I don't think there is a real difference. The interpretability instead, it seems crucial to me.
Yeah. I agree.
Okay, we'll take one more question, and then that's it for real.
So the question to Professor Farmer, you run a group for complex economics in Oxford. Is there any other groups around universities that do complexity economics?
There are a few. The main one in the U.S. is at George Mason University, the computational social science group that Rob Axtell runs. There's a few scattered people. Blake LeBaron at Brandeis does some nice agent-based modeling in financial markets. There's a significant group at the Complexity Science Hub in Vienna run by Stefan Turner, not just focusing on economics, but there is some economics there too. And then there's some groups like in Germany building agent-based models, and there's quite a few Italian groups too. Giovanni Dozzi's group in particular in Pisa would be the main one that I would think of. But so there's a few, not much.
Okay, well, I'd like to thank our speakers and Doyne. Thank you. Thank you all for coming.